So hello everyone. So in this video I am discussing the practical differentiator. So this is the circuit for practical differentiator. So this we have connected the resistor in series with this capacitor in the ideal differentiator circuit. So this is op-amp is ideal. So virtual ground concept is valid here. So there will be 0 volt and the transfer function, that is V0 upon Vn, will be of this form minus Rf upon this impedance, because the input is applied at the inverting terminal only. So V0 upon Vn will be minus Rf upon this impedance, that is R plus 1 upon Cs, which will be RCS plus 1 upon Cs. So it is R plus 1 and upon Cs. So the transfer function is minus Rf Ps upon RCS plus 1. We can see that there is a 0 at origin and one pole at minus 1 upon R. So the pole 0 plot like this. The pole at minus 1 upon R and there is a 0 at the origin. Right. So from this pole, we can clearly talk about the time constant. It is simply RC seconds. But I haven't mentioned the time constant in the ideal differentiator. So this is the ideal differentiator. And here we can see that this is an unstable response. Right? And for unstable response, the time constant we can say does not exist or not defined. So for ideal differentiator, time constant is not defined. But for the practical differentiator, the time constant is clearly defined as RC seconds. So this is the pole 0 plot. Now, what else we can say from this pole 0 plot? That this pole 0 plot is representing a first order high pass filter, because एक हाई पास फिल्टर का पोल 0 प्लॉट बेसिकली इस तरह से होता है कि जितने पोल्स हैं उतने ही ओरिजिन पर 0 लाई करनी चाहिए. सो बेसिकली एक फर्स्ट ऑर्डर का हाई पास फिल्टर का पोल 0 प्लॉट होता है, राइट. तो मतलब बेसिकली एक लो पास फिल्टर को अगर हाई पास फिल्टर में कन्वर्ट करना है तो जितने पोल्स हैं उतने ओरिजिन पर 0 से ऐड कर दीजिए, तो एक हाई पास फिल्टर कन्वर्ट हो जाएगा, मतलब एक लो पास फिल्टर, राइट. सिमिलरली वी कैन यहाँ से भी वी कैन सी दैट this at zero frequency the magnitude of this transfer function will be simply 0, means the low frequency is not passing. And at infinite frequency, because the order of numerator and denominator are same, so simply the coefficients will get divided. So the magnitude will be Rf upon R. It means the high frequency is passing and the low frequency is not passing, so that's why it is a first order high pass filter. So now for having the frequency response of this transfer function, so transfer function is minus RFCS upon 1 plus RCS. Now if I divide the numerator denominator by the CS, so it will be minus RF upon R plus 1 upon CS. So now if taken this R common from this denominator, so it will be minus RF upon R upon 1 plus 1 upon RCS. Now putting S is equals to J omega, so it will be minus RF upon R upon 1 plus 1 upon J omega RC, which we can write like this: 1 minus of J and 1 upon RC upon of omega. So why we have written like this? Because the general expression for the frequency response of high pass filter is this, because E0 upon 1 minus J and omega L upon of omega. This is the general frequency response expression of a high pass filter. This A0 is the maximum gain or maximum magnitude, right? And this omega L is the lower dB frequency. So by comparing these two expressions, this one and the, we can see that this A0 is a magnitude of minus RF upon R. So this is the maximum gain, and this omega L is 1 upon RC reading per second, right? Now we can draw the magnitude plot of this transformation. So we will write this transformation like this: minus RF upon R and upon 1 minus of J and omega L upon omega. So this magnitude will be RF upon R and upon 1 plus of omega L upon of omega whole square on interval. So for the zero frequency, the magnitude will be 0 because this will be infinite and Rf upon R are infinite. So it will be 0. At omega is equals to omega. This will be 1. So the magnitude will be Rf upon R divided by root 3. And at infinite frequency, this term will be 0. So magnitude will be simply Rf upon R. Right. So as we can see that as the frequency is increasing, the magnitude is also increasing. Means the gain or magnitude is directly proportional to omega. So the magnitude plot will be like this. So this is the maximum magnitude, and at the lower frequency, the magnitude is 1 by root 2 times the maximum magnitude. This is Rf upon R, and this is Rf upon R divided by root 2, and this is the omega. This is nothing but the 3 dB down. So this is the magnitude plot of practical differentiator circuit, and this practical differentiator circuit is equivalent to a high pass filter, and the and the practical indicator was equivalent to a low pass filter, right? So this is the 1 upon RC, and now this is the maximum magnitude or maximum gain. This is also known as the mid-band gain, and this is nothing but the high frequency gain of practical differentiator circuit, and the DC gain of a high pass filter is always 0. So the DC gain of practical differentiator circuit is 0, which is a very good point. Now this is the low 3dB frequency, and for high pass filter the higher 3dB frequency is lying at infinite. So this is the bandwidth, right? So this bandwidth is omega h minus of omega L, which will be infinite because the higher 3dB frequency is infinite. So this infinite bandwidth is actually the drawback for this of this circuit, that is the practical differentiator, because due to the infinite bandwidth it will accumulate the high frequency noise signal. So high frequency noise signal will also included in the circuit. So that's why this is a problem of this practical differentiator circuit. So for avoiding this problem, we used a modified practical differentiator circuit, or we can say the improved version of the practical differentiator circuit. So the modified practical differentiator circuit is, so this is the practical differentiator circuit, right? So now we will connect a capacitor in parallel with this resistor. Now this has become the modified practical differentiator circuit. So now for this transfer function, so these two will form an impedance. So this will, let's say this is the Z2 and this is Z1. So we can simply place this circuit as this one. This is the Z1 and this is Z2. Now the circuit has become a simple inverting op amp, right? Which V naught by Vn is equals to minus Z2 by Z1. So Z2 is the RF parallel with 1 upon CFS, which is RF upon RF PFS and plus 1. And Z1 is the series combination of resistor and capacitor, which will be RCS plus 1 upon CS. So V naught upon Vn of this inverting op amp, which will be minus Z2 by Z1, which will be minus RF, and this will be in the numerator CS upon RF CFS plus 1 and RCS plus 1. So the transfer function is minus RF PS and upon RF CFS plus 1 and RCS plus 1. So there is a 0 at the origin and there are two poles, one at minus 1 upon RFCF and minus 1 upon RC. Right. So if we see the magnitude at the 0 frequency, right? So the magnitude is 0, means the low frequency is not passing, and at infinite, now the order of denominator is greater than the order of numerator, and whenever the order of denominator is greater than the order of numerator, so at infinite frequency the magnitude will be 0. So it means the high frequency is also not passing. So whenever the both the frequencies are not passing, it means it is representing a band pass filter. It is passing a particular band of frequency, or to be more precise, it is a second order band pass filter. And first order band pass filter so exists in vehicle. There is no meaning of first order band pass filters, right? Now the pole zero plot of this transformation. So which pole is lying first? Either this or this. So this is the correct pole zero plot or so. Either this is lying at first and after that 1 upon RC, or first 1 upon RC and after that 1 upon RF CF and 0 at the origin. So first let me draw the magnitude plot of this transformation, that is the band pass filter. So the magnitude plot of band pass filter is like this. So this is the magnitude and it is having the maximum magnitude at the frequency, which is the this frequency is omega naught, and at this frequency, that is, this is the lower 3 dB and this is the higher 3 dB frequency. Right, this is how the band pass filter magnitude plot is known. This is the omega naught, this is omega h, this is omega L. This part is representing the high pass filter and this part represents the low pass filter. And so overall is the second order band pass filter. This omega naught is nothing but the geometric mean of this omega h and omega L, right? And this is omega h. This part from this part we have got the omega h because we have this was a circuit of practical indicator, right? And from where so omega h is 1 upon RFC, and this is the practical differentiator part. So here we have got the omega L, that is 1 upon RC, right? So this is 1 upon RHCF and this is 1 upon RC. Now from this is the P naught maximum magnitude and this is P naught by root 2. This is the PdB down. This is the PdB down, and we can see that this omega h is very greater than omega L, means 1 upon RFCF is very greater than 1 upon RC, means this pole is lying after this one. So it means the correct pole zero plot is this one. This is wrong, right? Now this is the bandwidth. This is the bandwidth. It is omega h minus of omega L, right? And this is the maximum magnitude, or we can say the midband gain, and right, but not this is not the low frequency or this is not the high frequency, because the low frequency and high frequency gain both are 0. So because the maximum magnitude are we are getting at the frequency that is omega naught, we can actually find this omega naught also by taking this magnitude of this transformation and putting this omega as equals to omega naught. Just say यहाँ पर this magnitude will be, this will be RHC omega upon RF C omega, and upon this will be now 1 plus RF CF omega, then it will be whole square, and then it will be 1 plus RC omega, then again whole square, and the whole under root, right? Now, the maximum magnitude will be at omega is equals to omega naught. So simply we'll substitute this omega is equals to omega naught. This is the maximum magnitude, which will be simply RF P omega naught and upon. So for this respecting values of RF, CF and this RC, we will get the maximum magnitude like this. And this will be 1 plus RC omega naught whole square and null. Right. And one more thing here that यहाँ पर from this condition we can see that this RC should be very very greater than RFCF, right? So this is the designing point of from the designing point of view. This should be the condition that this should be satisfied. That this RC should be very very greater than RFCF. So for the designing of band pass filter, this is from the designing point of view. So this is the second order band pass filter, and in fact, this band pass filter is also the frequency response of op-amp, right? This is also the frequency response of not op-amp, sorry. This is the frequency response of amplifier. The op-amp frequency response is like a low pass filter. So this is the frequency response of op-amp, and this is nothing but the uh, current response of series RLC network. This is also the current response of series RLC network that we study in the resonance part in network theory, series RLC. And this is also the voltage response of parallel RLC network. So there is a lot of discussion in this bandpass filter because this is one of the most favorite graphs of one of the most favorite topic of the electronics branch. So voltage response of this parallel RLC, and this is also the what we study in the control system, that is the lead lag compensator. So this is also the response of lead lag compensator. So this is mid-band gain. So this is the discussion of differentiator circuit. That is, first I had this was the ideal differentiator, and this is the practical and the modified practical differentiator circuit, right? So okay, thank you.